Hello, my name is Evan Asuncion, and along with Joseph Bolsenmeyer and Michael Zhang, we will be presenting our project for the SCUDEM modeling competition. Our project is titled One Final Push, modeling a bike throw during a cycling race, and this is problem B. We are coached by Major Welvin Lucero, and we are from the United States Military Academy. So before we get into our model, just a bit of background on what the bike throw is. So cyclists use bike throw at the end of the race to get a slight advantage. The rider stops pedaling, shifts him or herself backwards, and then thrusts all his or her weight forward. And this resulting force pushes the bike forward. You can see an example of this is Ruth Winder narrowly edged out Demi Vollering in the 2021 Brabantse Pidgeot Dames race. So in our project, we had three goals / purposes. First, what's the optimal distance that can be gained by a bike throw in a certain time interval? And going off that, when is a bike throw most effective? What time interval is the bike throw most effective? And our third goal is how does hand positioning affect the riders? You saw in the picture of Vollering and Widner that Vollering had one hand compared to Widner, who had two hands, and she was more stable on the bike.
So to transform our problem into a model, we're going to be using Newton's second law, which is acceleration equals net force over mass. And using acceleration, if we find acceleration, we know that is the second derivative of position, so we'll be able to find position through that. We'll be modeling the whole process, whole bike throw through a piecewise function, as different forces will be acting on at different times. And assuming initial conditions, we will use the gsolve command and Wolfram Mathematica to find the position function. So before we can fully transform our problem into a model, some assumptions to make. The first one is that the initial speed is going to be 12.5, which is going to be before the bike throw. We're going to assume the two cyclists going at the same speed for the bike throw. And then we're going to assume that the bike during the bike throw moves 0.335 meters relative to the rider. And we're going to assume that this happens at 5 miles an hour, and the average output from this is 25.35 watts. So now for our piecewise function, the first piece of it will be 12.5 t, because we're assuming that there is no acceleration during this time, which is before the bike throw, and the initial velocity, which will end up being velocity throughout the whole time, will be 12.5 meters per second. The second piece will be the position function based on the forces acting on the bike during the throw, and that will happen from when t is greater than a and less than a plus 0.075. And the reason why it's that duration is because that is the calculated time for a bike throw to actually be executed. And then the last piece of our function will be the position function based off of forces after the bike throw. So for our parameters, we are assuming that mass is 55 kilograms, which is for the rider. We calculated F of push from the watts we found in our assumption. And then using constants we found online, we were able to calculate the drag force, which would act opposite in the direction of the bike throw.
So with all the parameters that we assumed, we can now create our piecewise function. As you can see, this is what we looked at when we plugged the values into Mathematica. So after we solve these equations, we can now plot and interpret. So here you can see the red line is the bike with the bike throw compared to the blue line without the bike throw. As you can see, before 5 seconds, they are going the exact same speed and therefore the exact same distance. But after 5 seconds, where that bike throw happens, the red gets an advantage in really a minute distance in millimeters. but it takes about 0.6 seconds for the red line to lose its lead and for the bike throw to stop becoming effective. So if you add that to the time it takes to execute the bike throw, we recommend that you should start the bike throw about 0.675 seconds before the finish of the race. And then to see the effects of how a lead would change if the rider who did not do the bike throw had a significant lead, how much of that lead could the bike throw make up. So by doing that, we just change the initial condition of the rider with the bike throw. You can see in the image on the left there, x of 0. We changed that up and basically guessed and checked until we saw that the max value, which the red stays ahead of the blue for literally, it could be like a tenth of a second slow, so very slow and very minute time intervals. But ultimately, we decided that approximately 0.32 meters was the maximum distance that can be made up by the bike throw.
All right, so interpreting the graphs, the bike throw is a very effective means to take in order to get that last little bit of distance in order to win the race. The only problem with this is you have to execute it at a specific time interval in order to reach its maximum potential. So, according to our graphs, the best time to execute the bike throw would be 0.675 seconds before the finish line, because after this time, you will start to slow down due to the lack of pedaling force and the shift in motion you are required to take in order to get back on top of the bike after the bike throw, which will increase your cross-sectional area and overall drag force. So while the bike throw is an effective mode of action to take in order to get that last little bit, there are contributing factors that can make it even more beneficial, such as your hand placement on the bike and your body positioning on the bike. For example, if your hand positioning is a little bit wider, while you may have a little bit more stability, you're actually decreasing the amount of distance covered by the bike throw because now your arms will not go as far, and also your cross-sectional area will increase, which will decrease your velocity due to the increase in drag force. So while you may have more stability with that wider grip, having your hands a little bit closer and taking that risk with stability is actually better because you can get more distance and more velocity. Additionally, your positioning on the bike with your body can be used to make it more beneficial. When you're closer to the bike, the aerodynamics and air resistance will decrease because you will be closer to the bike and your drag force will decrease. And also, when you're shifting back up onto the bike, it will be a faster process since you are closer to the bike. So while our model did show how effective the bike throw was, there are some limitations. First, our model overgeneralizes the bike throw in general because we assumed that it's based off of women due to the scenario we were given. So everything such as the arm's length, weight of the rider, all of those parameters were based off of women, so this may not apply to all scenarios. Also, we did not account for the shift in the center of gravity to help assist in the bike throw. So when you shift your weight backwards, we didn't account for that increasing the velocity or time of the bike throw. We just took the 5-mile-an-hour punch. Also, we did not account for any external factors, for example, the wind or any additional friction or weather that could account for an increase in drag force. Lastly, we assumed that the arm's length was 0.335, which may not apply to all racers or cyclists. We just took the average, so it may not be as precise and accurate in this situation. So this concludes our presentation. Thank you for watching. And here's our bibliography slide that shows where we attained all of our information regarding the cyclist problem. Thank you.